Let's look at an example here where we can use differential equations to help us talk about position functions, velocity functions, and acceleration functions. Before we do that, though, remember that if I want to talk about the velocity function, that is the first derivative of our position function s, and if I want to talk about the acceleration function a, that is the first derivative of the velocity function and the second derivative of the position function. So we can use this information to help us solve initial value problems involving motion. So here, for example, I'm given an acceleration function. It says, here's my acceleration function. It is 2 cosine of t. I want to find the position function. So I would like to end up with what is s of t here. So if I want to find the position function, I'm starting with acceleration. There's no way that I can jump straight from acceleration to my position function. I'm going to have to go from my acceleration and find my velocity function first, and then once I have that, then I can find my position function. So this is really a two-step problem. So first, I have the derivative. Essentially, this is the derivative of velocity, so I would like to find the antiderivative of 2 cosine of t dt. So first I'll find my antiderivative. Let's see, I should have 2 sine of t plus c. And yes, 2 sine of t, if I take the derivative of that, I would have 2 cosine of t. So this is my velocity function, v of t. So v of t, and actually let me just rewrite this so that I have a little bit more room. V of t is equal to 2 sine t plus c. And I need to find out what is this initial, or what is my constant of integration. And I'm given this initial condition. It says, hey, v of 0. So if I take 0, plug that into my function, 2 sine of 0 plus c, that is equal to 1. So now I have this equation that I can solve for c with. I know that sine of 0, that's just 0, plus c is equal to 1. So I have 0 plus c equals 1, which means that c is equal to 1. So my velocity function is v of t equals 2 sine of t plus c, which is 1. Here's my velocity function. But that's not where I want to stop, because I was asked to find the position function. I'm looking for what is s of t. So right now I have v of t. I want to take an antiderivative one more time to find, to find s double prime. So I want to integrate the function that I just found, 2 sine of t plus 1, and I'm going to integrate with respect to t. So let's see, this time I should have negative 2 cosine of t plus here, remember this is t to the 0, so plus t, plus I'll have a new constant of integration. You can call it c if you want to. I don't really like to call it c because I've already used that variable, so I'll just say, how about d? And this is my position function, or part of my position function, because now I need to know what is this d here. What is my constant of integration? So I'm told that s of 0 is equal to negative 2 cosine of 0 plus 0 plus d, that is all, equal to 0. So now I have this equation in which I can solve for d. So this is negative 2 times 1 plus d is equal to 0, so I end up with d equals to 2. So my position function then is s of t equals negative 2 cosine of t plus d, which we just said was 2. Here is my solution. So really similar to the other initial value problems that we were doing in the last video, I really just have kind of a two-part process now. So if you start with acceleration, you need to work your way backwards to find your velocity function first, and then once you have that, then you can go ahead and find your position function. Be careful with some of these in the homework. Sometimes they will give you the acceleration function. You may have instances, though, where they just start off by giving you the velocity function, though. So just make sure that you're paying attention. You know exactly which function you are starting with. Are you starting with acceleration or are you starting with velocity? Let's look at one last example before we wrap this section up. It says begin with the acceleration equation a of t equals v prime of t is equal to negative g, where g is 9.8 meters per second squared. This is just the acceleration due to gravity on Earth. It says a stone is thrown vertically upward with a velocity of 30 meters per second from the edge of a cliff 200 meters above the river. Part A says find the velocity of the object for all relevant times. So we want to find the velocity. We have the acceleration. So the acceleration function right now is negative g, and g is negative 9.8. So I have acceleration. I would like to find my velocity here. So I need to integrate my acceleration function. So I'm going to integrate negative 9.8. T is my variable, so with respect to t. And this is just a constant, so not a whole lot interesting is going to happen. I'm just going to pick up a factor of t, so negative 9.8 t, because again, remember that this is really negative 9.8 times t to the 0 power. That's where I'm getting that from. And then, yes, of course, plus my constant of integration c. So this is my velocity function v of t. But I'd like to be able to say what my constant of integration is for this problem. What is c? So they give me some information here. They say a stone is thrown vertically upward with a velocity of 30 meters per second. I'm going to stop right there. So that means when I've thrown the stone upward, when time t is equal to 0, my velocity is 30 meters per second. In other words, when t is equal to 0, my velocity is 30. Another way I could write that is v of 0 is equal to 30. This is the initial condition that I need in order to solve for c. So let's see, v of 0, this is negative 9.8 times 0 plus c is equal to 30, which means that c is equal to 30. So my velocity function is negative 9.8t plus 30. Here is my velocity function. So, okay, cool. I've answered part A. I have my velocity function. Now, in part B, it says, well, now go find the position function for all relevant times. So if I want the position function, I want to find the antiderivative of the velocity function that we just found, which is negative 9.8t plus 30 dt. So again, I'm integrating with respect to t. I want to find the antiderivative. I'm just taking my velocity function here and finding our antiderivative. So here, adding 1 to the power negative 9.8t squared divided by 2 plus 30t plus a new constant of integration. How about I call that d? So I should end up with negative 4.9t squared plus 30t plus d. And again, I'd like to be able to say what is this constant of integration. So let's go back to our problem, because that's where we got the initial condition for velocity. So let's see, we throw the stone vertically upward with a velocity of 30 meters per second from the edge of a cliff 200 meters above the river. So that means, if I kind of take this information, when t equals 0, we are 200 meters above the river. So my position function s is 200. So in other words, s of 0 is equal to 200. So this gives me a means to solve for d. So s of 0 is equal to negative 4.9 times 0 squared plus 30 times 0 plus d. This is equal to 200. Ends up giving me d is equal to 200. So I have my constant of integration. I just need to plug that back into my position function. So I'm running out of room here. S of t then is equal to negative 4.9 t squared plus 30t plus 200. Here is my position function. So not all that different from the example that we just looked at right before this. And we may want to do a little bit more work here. Part C says find the time at which the object reaches its highest point and what is its height. So here, if I want to find the time at which the object reaches its highest point, you can think about this a few different ways. Highest point. That makes me think of a maximum of my position function, s of t. So essentially I'm looking for a maximum of the position function s of t. So we can still use what we know about derivatives here. You could look at this and say, okay, that's a quadratic. We're going to use the vertex formula, but there's no fun in that. I'm going to take the derivative of my position function, which we actually have. We had that as the velocity function, which I actually have conveniently written in blue right here, negative 9.8t plus 30. Negative 9.8t plus 30. And I'm going to see if I can find the critical points of this function. So negative 9.8t is equal to, negative 30. Jumping ahead of myself here. Let's do this. Here's my derivative. I just want to set it equal to 0. That's a lot easier. So I have 30 equals 9.8t. So let's see, t is equal to 30 over 9.8, which you of course know. You would say, of course, well that's just approximately 3.06. So this is when it reaches its highest point. And actually I should pause right here and say, well, maybe, because I don't know if this is a maximum or a minimum, or perhaps neither one. So I may want to double check using either my first or second derivative test. For this function, since we already have the second derivative, so s double prime of t, we said that was, just negative 9.8 up here earlier. So s double prime of t, that is a of t, that is negative 9.8. So s double prime, if I take my critical number that I just found, 3.06, plug it into my acceleration function. These two are just different notations for the same thing. It's a constant function though, it's just negative 9.8. And I think about what this tells me, because I'm trying to do the second derivative test here. So the second derivative is negative. What does that tell me? It tells me it's concave down. It tells me that I do in fact have a maximum, and that's exactly what I wanted. So okay, I know that I achieve my maximum, and actually let's just make a note right here. The max height at t equals 3.06 seconds. And then it says, what is the height? Well, for that, I'm just going to be looking at the position function. So what is the maximum height? If I wanted to calculate that, height, oh boy, I can spell. If I wanted to find the maximum height, I would take this 3.06 and plug that into my position function. So that would be, let's see, negative 4.9 times 3.06, and I'm going to run out of room. I need more room. This would be negative 4.9 times 3.06 squared plus 30 times 3.06 plus 200. And then, oh boy, I don't know what happened there at all. I apologize. iPad is not excited to finish this problem. We were right here. We were looking at our position function, which ended as plus 200. There we go. And then you would just go and calculate whatever this value is. I'm not going to do it because I don't really want to, but you would go and calculate that value. Similarly then for part D, it says find the time when the object strikes the ground. So when it strikes the ground, that's really another way to say when the position function s of t is equal to 0. So let's see, here I'm going to take my position function, which is negative 4.9 t squared plus 30t plus 200, set this equation equal to 0, and solve. So you could try and factor it, but it doesn't look like you're going to have a really good time factoring that. Actually, you might be able to do that. I don't want to go off on a wild goose chase on something that I may or may not be able to factor, so if it were up to me, I'd probably just say, you know what, let's just use the quadratic formula here. So t equals the opposite of b, so negative 30, plus or minus square root of b squared, so that's negative 4.9, oops, nope, b squared, not a squared, b squared, that is 30 squared, minus 4 times a, that's negative 4.9, times c, that is 200, all over 2a, that's 2 times negative 4.9. So let's see here. I know I'm going to end up with two answers here. One should be negative, so I can discount that value. Let's just go through this really quickly. 900 minus 4 times negative 4.9 times 200. I wonder if this is going to be a perfect square. So I end up with 4,820 under my radical over negative 9.8. Let's see, radical 4,820. No, it wasn't. Oh, well. So I have negative 30 plus or minus 69.43 all over negative 9.8. Oops. And then I'll have negative 30 plus 69.43 divided by negative 9.8, and negative 30 minus 69.43 divided by negative 9.8. Be careful you work these problems to the end, because we're dividing by a negative here. You will want to make sure that you're looking at the positive solution. So negative 30 plus 69.43, oops, 69.43 divided by negative 9.8. Here, over here, I ended up with negative 4.02. That doesn't make sense because we're talking about time. Time can only be a positive quantity. So we must be talking about this right-hand term, negative 30 minus 69.43 divided by negative 9.8 gives me roughly 10.15 seconds. So after about 10 seconds, our rock will hit the ground or hit the river, wherever it lands. So these last two parts should feel really familiar because these are the types of problems that we looked at way back in chapter 3. So we're just kind of have a new starting point. We're saying, okay, if we start with acceleration, can we build our way to position? And then, oh yeah, maybe let's go ahead and review some of those main ideas from position, velocity, acceleration, knowing what they're asking and how they're related.